Today's session, I think it is really brainstorming session because as soon as this GAN course started, everybody was in, I think you might be on Google, that what is this fluorine chemistry, how many drug molecules are there, how many percentage drugs are having fluorine, and then everyone feels like, okay, I will also have some fluorine molecule, I will synthesize it, I will get good paper. And once you come here, then Professor Altman, he mentioned that what you are feeling, that it is a isoster of hydrogen, that's not true, and it has little bit different properties, different size. Then Dr. Deepak, he showed you so many drug molecules, and at the end, when like it was very promising picture and we think that okay, we'll also have such kind of molecule, he mentioned that how it gets metabolite and it might have some adverse effect. Okay, so what now we learn from all of this is whatever we are going to plan, we have to plan it wisely. And obviously all of we know that whenever it will go in market, there is a long process. So anyway, that will be taken care. But since if you want to introduce fluorine, how we can how we can introduce it, or what are the reagents we have, so that we are going to discuss now. Okay, so I will skip this slide because you already know there are so many drug molecules and they have variety of fluorine atoms. So, and one more thing, I would like to thank Professor Altman because when I was preparing on this topic, he very kindly shared his material with me. So for me, it became very easy to prepare this talk. So for introduction of fluorine, there are two ways or two methods. You can see here A and B. So A is called as a traditional way, in which what we do, we take starting material which already has fluorine atom, and then we club it with other molecule and do little bit modification, and then our molecule is ready. But this approach is not very feasible because suppose you want to do SAR or you want to introduce fluorine at many places, then you need different starting materials, right? So every time you have to find out molecule which has fluorine, and that component you have to club. So that is not very feasible. So another approach which is called as advanced method. In this advanced method, what we can do, that we have our desired pharmacophore, or since you are students which are interested in drug discovery, so you have molecule and then somehow you can replace this CH with fluorine. So you have many reagents which directly replace this hydrogen with fluorine, and that we are going to see. Another way is you convert this H into some other functional group, right, like halides or OH, and then you do fluorination. Okay, so for this path A, you need some reagent which is a source of F minus, so nucleophilic fluorinating reagents. Another way is you can have some carbon metal bond, and then you can use some electrophilic reagent which is a source of F plus, and then you can introduce fluorine by that electrophilic reagent. So basically these are the two types, nucleophilic and electrophilic fluorinating reagents. In nucleophilic fluorinating reagents, again you have alkali metal fluorides, tetraalkyl ammonium fluorides, and there is one different class which is called as a deoxygenating fluorinating reagent like DAST. Okay, so where you will replace OH directly with fluorine. Now in this talk I will not cover the reagents which will be used to get CF3 or CHF2 or CF2H in your molecule. So basically most of the reagents are for the introduction of single fluorine atom. So you have these electrophilic reagents. Okay, you can see here these are electrophilic reagent, and if you observe this structure, basically they have nitrogen fluorine bond. Okay, and you have another class of compounds which are nucleophilic reagent, in which there is a sulfur fluorine bond or carbon fluorine bond. So whenever we are going to use reagent in our day-to-day practice to get fluorine in our molecule, what we will see for process chemistry, people they think more about yield, cost of the reagent, and impurity profile of product. Okay, so means if it is giving you some other byproducts or something like that. In medicinal chemistry, it is more about availability of your starting material and can you do it, introduce fluorine in later stage, okay, so that there is no much problem. So these things we have to keep in our mind, and accordingly we have to use reagents. There are, I will show you n number of reagents are there to introduce fluorine, okay. And why this is so, like Dr. Deepak mentioned you that in last decade there is a huge increase in number of drug molecules which has fluorine. So there was continuous pressure on organic chemists that you have some methods which will be easy to introduce fluorine. So from that point of view, many methods have developed which introduce fluorine in organic molecule in simpler way. Okay. So first I will talk about fluorination of compounds which are aromatic in nature, okay, and these are pre-functionalized aromatic compounds. In this compound you can convert aromatic amine to corresponding diazo compound, and initially this Ball-Schimann reaction, this was used for this purpose, and this diazo compound was isolated, and then by nucleophilic displacement we can get aryl fluoride. Okay, so you can see there are so many compounds where fluorine has introduced. Now, this Bookwood and co-workers, they developed new method in which there is no need to isolate these diazo compound. Okay, so they have not isolated it immediately. They have done fluorination, and it has enhanced the yield of this reaction. Okay, so this is a very good modification they have done in this reaction to get fluorine on aromatic carbon or sp2 carbon. Okay, the halogen exchange reaction is another example in which again you can get fluorine on sp2 carbon of your aromatic ring. So for this purpose, this tributyl ammonium fluoride, it was generated in situ by reaction with tributyl ammonium cyanide with reaction by reacting it with hexafluorobenzene. Okay, so you can get this compound in situ, TBAF, and that you can use for fluorination. So this reaction again it gave excellent yield, and you can do that reaction in room temperature. Okay, so that is again very good method. So one more method to get fluorine on sp2 carbon or fluorine on aromatic ring is by replacing OH group like phenolic group by fluorine. Okay, so this can be done by phenofluor. So name itself suggests that phenol is getting converted into fluorine. Okay, so for that purpose you have this 2,2-difluoro-1,3-diaryl imidazoline ring. Okay, so this kind of compound you have which you can use for fluorination, and again this reaction is used to displace OH on aromatic ring to get fluorine there. You can, if you do fluorination in case of electron-rich aromatic system, heteroaromatic system, usually you get fluorine at third position. Okay, if you want to get fluorine at second position, then what to do? So you can use this carboxylate, okay, at second position, and then you can easily introduce fluorine at that second position. Okay, so this is another method. So far we have discussed the few methods by which you can introduce fluorine on sp2 carbon of aromatic ring. There are huge number of reagents which use transition metal catalysts to do this reaction, but I will not talk about that. Dr. Ravi will talk about that topic maybe tomorrow or day after tomorrow. So now we will shift towards fluorination on aliphatic substrate. How we can get fluorine on aliphatic substance. So we can do that by using alkyl halide or alkyl triplet, means you have some good leaving group, right? And then you can use nucleophilic reagent which will displace that leaving group, and you can get fluorine. Okay, but problem with that, whatever nucleophilic reagents I have mentioned in earlier slide, those are either metal fluorides, so solubility issue is there. So cesium fluoride is better soluble. Again, if you want to use KF, potassium fluoride, then you have to use phase transfer catalyst. Okay, or then you can use this TBAF, tetra-alkyl or tetrabutyl ammonium fluorides. That will increase the solubility. Those are soluble in organic solvents, and you can use such reagents. Or you can use compounds like tri-tertiary butanol amine. These compounds can be used as organic promoter, and it will help to increase the yield of your fluorinated compound by eliminating, by reducing the amount of elimination product, right? Because you have learned that whenever you want to introduce fluorine, sometime you get double bond there. That gets HF gets eliminated and there is a double bond. So that can be reduced by using such kind of promoter. So this is one method in which you can introduce fluorine on aliphatic substrate. Another method, you can use such kind of catalyst, and you can again use that catalyst along with KF, and you can do nucleophilic displacement. You can displace OTF, O triplet, and you can get fluorine there. So these are the methods for introduction of this fluorine by displacing it triplet or some halides, okay, bromide or iodide. You can use one more reagent which is called as a dust, and I think everybody knows dust because this is somehow very famous reagent of chemist. Okay, actually this reagent has few problems. What is the problem? It undergoes non-energetic disproportionation, so it will form this SF4 sulfur tetrafluoride and this bis ethyl amino sulfur difluoride. Okay, this further it will degrade and it is explosive in nature. So handling of this reagent, there is a little bit problem, but still it is a very good reagent because it gives very good yield. Okay, so you can use dust. And how it works? So if you have alcohol, that OH will be replaced with fluorine, and most of the times you get inversion in configuration, but there are reports where you have retention of configuration, or in some cases there is a rearrangement. Okay, so you have to remember that also. So initially this OH, it will attack on this sulfur, right? Sulfur of this dust, and F minus will go out. Then lone pair of nitrogen, it will form sulfur nitrogen double bond. Again F minus will go, and that F minus will attack from backside, and so that you will get SN2 kind of reaction with inversion. Okay, so you will get fluorine with inversion. Whatever OH was there, exactly opposite stereochemistry will be there for fluorine. Okay, so there is another method in which, okay, where this fluorination is done of this aliphatic OH. Okay, so here also they have used dust, and what you observe that you get inversion in configuration as a major product. So 31% you got this compound, but you will also get a compound with retention in configuration, and there is also rearrangement product. Now why it is so? Because there is a formation of this transient aziridium ion. Okay, so this will form. So whether it is your medicinal chemistry or organic chemistry, you have to always look up around your reactive site, that how it is going to alter your way. Okay, you are desiring something, and if you are not getting, you have to see, or initially only you have to say that okay, here it is there, so it might affect the stereochemistry. Okay, so you will see that even though inversion chemistry, inversion compound you have major, you are getting another two compounds as well. And sometimes people don't mind if you get such kind of other compounds, it is good, you can have diverse library of molecules. Okay, so you can use that library. So that's what it is done for this case. Okay, so this fellow has done so many fluorination reaction on different, slightly different starting materials and got different compounds. Okay, so that is a library kind of thing. Now dust also used to get fluorine in 7-member ring. Okay, so in azipanes also you can get fluorine instead of OH. But now if you see here stereochemistry, you are getting here fluorine with retention of configuration. Now it is because of this Bock group which is acting in neighboring group participation way. Okay, and that's why there is a double inversion, and that's why you are getting retention here. Okay, now similar system you have in this compound also, but now your compound is having double bond. Okay, so since it is having double bond, now that neighboring group participation, it is not that much feasible, because you will have that fused system, and in fused system it is 5 fused 4 kind of thing, and then it becomes a little bit rigid system. Okay, so you can't have double bond. So neighboring group participation is not much, and that's why you are getting, even though this Bock and OH are like 1 carbon away from each other in both the cases. Here also you have 1 carbon, here also you have 1 carbon. But here dust is giving you compound with retention in configuration, and here it is giving you compound with inversion in configuration. Okay, so this is because of here neighboring group participation of Bock is there. In this case it is not possible. Okay, Now again, this is very important. Whenever you have fluorine and in consecutive ways, it will affect conformation. So this is an example of synthesis of alpha, beta, gamma, trifluoro, delta amino acids. So you have these 3 fluorine atoms, right? And if these are all syn, then it will have bent kind of geometry, okay? And if you have syn anti, then there will be zigzag geometry. Conformation will be different. Now how to get these two compounds? So initially if you treat this compound with deoxofluor, actually what you have to do, this somehow you have to remember names, because I'm going to use these reagents again and again, okay? So you have to remember those names, and then it will make sense to you, okay? So we have to use deoxofluor. It will again do displacement reaction, and we are getting here fluorine. Again, it is a dust kind of similar class of reagent. So you will get inversion of configuration. Now, as I mentioned in the beginning itself, that dust, even though most of the times you observe retention in configuration, sometimes you get, inversion in configuration, sometimes you get retention in configuration, okay? Now here carbocation formation is prevented due to presence of this nitro group, right? Because it will not stabilize that carbocation at benzylic position. So that's why you are getting only SN2 product. Again, this TMS morphylin, it will stabilize, it will prevent SN1 path. So that's why you are getting fluorine with inversion in configuration. Now for this epoxide opening, you have to do a little bit strong condition, microwave irradiation you have to do with triethylamine and hydrogen fluoride. So you will get this compound, okay? Again, this fluorine attacks at this position or that position, that doesn't matter, because anyway your final product in that two will be same, okay? It is going to, here also if it attacks, as I shown you, it is at by beta way. If it attacks at this position, again here also it will be beta. And then you are again using deoxofluor, so inversion in configuration, and you are, whatever this alpha OH, that will be replaced by beta fluorine. Okay, so you are getting here anti-syn conformation of 3 fluorine atoms. If you want all syn, then first you have to do Mitsunobu reaction. You have to invert that OH and again follow same sequence. You will get all syn 3 fluorine compound. Okay, so that's how you have to do these reactions. Now synthesis of dipeptyl peptidase. Okay, this is a very good inhibitor for the type 2 diabetes, and in this it has shown that how DAST is used to introduce fluorine. Okay, so 1.1 to 1.2 equivalent of DAST at minus 78 degrees Celsius, you can get 70% of yield of this compound, and further on transformation you can get your desired this peptidase compound. Okay, now another class of compound, that is fluoroamino reagent, which is also called as a FAR. Okay, so in this you have this fluoro and dialkyl amine group, and this kind of reagent are used for the displacement of OH, and at the place of OH you will get fluorine. Okay, so these are the reagents which you can use in your synthesis. So here you can see that deoxyfluorination using this FAR reagent, you can convert epoxide to corresponding difluoro compound, or you can convert 1,2-diol to fluoro compound. Okay, fluoro, and you have here ester group, which later you can hydrolyze, and you can use one more reagent and you can introduce fluorine here also. Now extal fluor, again this is one more reagent, and it is also used to introduce fluorine, and you can displace this OH and you can have fluorine with inversion of configuration. Okay, so this is a dialkyl amino difluorosulfinium tetrafluoroborate salt. Okay, so this is a salt, and since it is a salt, it is a crystalline bench stable compound. Otherwise, you know that dust, it is difficult. Initially I told you that it will undergo disintegration and it is explosive. So handling becomes a little bit difficult, but you can use, now such a reagents are there, so you can use these reagents and it will do same work for you, like it will replace OH with fluorine. So you have this reagent as well. Now here if you use external source of fluoride, that F minus from external source you will attack here in SN2 fashion, and you will get fluorine. If you are not using that external fluoride source, and if you are using base, then this base will promote hydrogen here. It will form sulfur nitrogen bond, and then F minus will be ejected, and that fluoride ion will attack here, and you will get fluorine with inversion in configuration. Okay, so these we are just seeing different reagent. Like few reagents, there is some problem with solubility, stability, and then you have advanced reagent. Like with initially we talked about KF, you have to use phase transfer catalyst. Okay, so instead of that, you use some tetrabutyl ammonium fluoride. Okay, so instead of that, again that will solve problem of solubility. Okay, so like that you have different reagent. So you will do something, you will face problem, and then there is another reagent. So you should know about all these reagents. Okay, now flow lead, again this is a new reagent, and it is a refined version of phenyl sulfur trifluoride. Okay, so this is your reagent which is called as a flow lead. It will also do introduce fluorine, and instead of OH you can have now fluorine. Okay, so flow lead is easily accessible in high yield, and you can prepare it or you can get by reaction with zinc chloride with 3,5-dimethyl tertiary butyl benzene with S2Cl2. Okay, so if you treat this compound, you will get this, and you can use that reagent to get fluorine in your molecule. So it is a shelf stable, and it is easy to handle crystalline solid. Okay, so it has advantage over dust. Phenofluor. So we have discussed earlier that phenofluor, it is generally used for displacement of phenolic OH group, and you can get fluorine there. But you can also displace OH in aliphatic substrate, and you can get fluorine there. Okay, so this is a phenofluor reagent. Again, it has structure like this. We have initially seen the structure. Okay, so this lone pair of nitrogen here, it will attack, it will form carbon nitrogen bond, F minus will come out, then OH will attack here. Okay, so you will get this kind of intermediate, then base will abstract this proton, and again this lone pair of nitrogen, it will come in picture. There is a formation of carbon nitrogen double bond, F minus will get eliminated, which will attack by SN2 fashion, and you will have now alkyl fluoride. Okay, so this you can use for displacement of aromatic OH, it can be used for the displacement of aliphatic OH as well. Now, phenofluor is very good. You can see that there are 1, 2, 3, 4, 5 hydroxyl groups, but selectively it will fluorinate only this OH, which is in red color. Okay, because this is a tertiary OH group, and rest of the OH are forming hydrogen bond. So it will selectively fluorinate this hydroxyl group, and this is used in synthesis of these many drug compounds. Okay, so you have variety of compounds in which you can have this fluorine here. Okay, so this is the advantage of late stage fluorination. Okay, you can do at the late, they have functional group tolerance, so you can do that fluorination without affecting other sites in your molecule. Okay, so deoxyfluorination using this pyridine based compound. Okay, now nitrogen of this pyridine heterocycle, what will it will do, it will have electron withdrawing inductive effect kind of thing, and that compound, this pifluor, you can use again for the displacement of OH with fluorine, and it is shown here that it can be displace sterically less hindered OH group. Okay, so you can have here means initially it was there a OH group which is secondary OH group, and you have tertiary OH group, but it only displays secondary OH group. You can also displace OH by keeping intact carbonyl group. Okay, so this is again another very good kind of reagent which you can use in your synthesis. Deoxyfluorination using CP fluor. So right now, till now, whatever reagents you have seen it has either nitrogen fluorine bond or it has sulfur fluorine bond. Now this is a cyclopropene which has this 2 fluorine atoms here. So this is the first all carbon kind of reagent which is used for fluorination. So this also displays OH, and you can get fluorine here. So again, this kind of reaction is observed with inversion of configuration. Fluorination of several steroid derivatives in which complete retention was observed. Okay, so even though it gives retention, if you are working with steroids, it will give you retention in configuration. This is due to homoallylic participation. Okay, so this you have to remember. Again, that CP fluor, cyclopropene based fluorinating reagent, it is used for the fluorination, and here it is displacing this primary OH group with this fluorine compound. Okay, in some cases unusual selectivity was also observed, means secondary OH group will be displaced instead of primary. Okay, so it is not hard and fast that always it will displace primary. It vary substrate to substrate and what the neighboring atmosphere in that molecule. If we see the reactivity trend, then electron rich benzylic, that will displace more compared to secondary, then electron deficient benzylic, primary, and electron deficient secondary OH group. Okay, so this is the trend. So you have to see that in your compound what kind of OH group is there and which OH you want to displace. Okay, now you know that dust will displace this carbonyl with gem difluoro compound. Okay, you will get geminal fluoride here by dust. But if you are using this carbonyl compound and if you are using this tosyl hydrazine, it will form hydrazone and you will get here only one fluorine atom. So it will be addition of you can say hydrofluorination of carbonyl compounds. Okay, instead of two fluorine, you are getting hydrogen and fluorine at that place by first converting this ketone into hydrazone. Okay, so again means no need to, if you don't want to have two fluorine atoms here, don't use dust. You have to follow this sequence, then you can get only one fluorine atom there. Now for this kind of reaction where you want to fluorinate alpha position of aldehyde, you have to use electrophilic reagent, because all of you know that these protons are acidic, it will form that carbanion here and then you can use electrophilic reagent, you will have this fluorine here. Okay, but this is a little bit difficult because there is a competition of homoaldol reaction. Okay, but this you can do by selective fluor and you can get 73% of yield. But here there is, we are not talking about stereochemistry. If you want that enantiomeric compound, then you have to use some catalyst, and with that catalyst you can get, so with S-proline only, here also S-proline is used. Here with S-proline, if you see enantioselectivity is only 29% enantiomeric excess. Okay, again this is by using this reagent select fluor. Okay. Now again asymmetric alpha fluorination of aldehyde, you can do that by using this NFCI, N-fluorobenzene sulfonamide reagents. Okay, again these are electrophilic reagents, so you will have this in all kind of thing and then you can introduce this fluorine. Okay, so if you use this kind of a catalyst, you will get 96% yield and 99% enantiomeric excess was reported. Okay, so you can do fluorination in an asymmetric way also. Okay, so like sir has discussed that it is when you are having fluorine in drug molecule, you have to be very careful about stereochemistry. So asymmetric synthesis of this fluorination is very important, so that you can do by this reaction. Okay, so similar you can do for this compound also. Again you have to use NFSI reagent and you will get 85% yield and 98% of enantiomeric excess. Asymmetric fluorination of ketone via enamine formation using cinchonalcolide. Okay, so formation of this alpha fluorine compound, alpha to ketone carbonate, it is little bit difficult as compared to aldehyde, but that can also be done by using this kind of alkaloid. Again it will form that kind of hydrazone and then it will allow that fluorine only from one specific way, and that's why you can getting only one fluorine with that particular stereochemistry. Okay, and this is used for the synthesis of these compounds. I think this EC is not on. Okay, so asymmetric oxidation fluorination of aldehydes. So again we are seeing asymmetric oxidative fluorination. So here what we are seeing, aldehyde group, it is also getting converted into carboxylic acid and further it will form ester, and you are also getting fluorination at alpha position of this carbonyl compound. Okay, this can be done by using again NFSI, this kind of reagent, and you have to use catalyst like this. Okay, so whenever you know that some chiral auxiliary you have to use whenever you want to do asymmetric fluorination. So that kind of catalyst you have to use here. Sun's asymmetric oxidative fluorination of aldehyde. Okay, so again here means NFSI, it is introducing fluorine at alpha position. It is also acting as oxidizing reagent. So that's why aldehyde is getting converted into corresponding methyl ester. Okay, so this is reaction you can do with 1.1 equivalent of methanol. Okay, so you will get this again obviously you have to use this kind of a catalyst. Zakarian stereoselective alpha fluorination of N-acyl oxazolidine. Okay, so this is N-acyl oxazolidinone. For this compound, if you want to do fluorination at alpha position of this carbonyl, you can do with some reactivity of metal enolates. Okay, so you have to form that enolate, and that metal enolate further it will react with NFSI, which is electrophilic reagent, and you can have this fluorine here. Okay, and if you use some catalyst like this, you can get diastereomeric selectivity 93:7%. Okay, so you have to remember these things. Macmillan, now here he has used visible light mediated decarboxylative fluorination. Okay, so catalyst used was this, and instead of this carboxylic acid group, you have now fluorine here. Okay, and this can be done in presence of visible light. So you can have this 34-watt blue LED as that UV source, and you can do this reaction. And so many other substrates, they have seen reaction on this substrate where this carboxylic acid group was displaced with fluorine. Okay, so you have to again keep these things in mind. Silver catalyzed decarboxylative fluorination, again you can do this decarboxylative fluorination by using silver catalyst. Okay, first we have seen this iridium catalyst. Now you can use this silver nitrate and selectofluor, which is again a fluorinating reagent, and you can have fluorine instead of this carboxylic acid group. Now you can do aminofluorination, means if you have alkene, you can do addition reaction kind of thing, and you can have this amino group here and fluorine group here. Again, if you use palladium catalyst, you will get this kind of compound. So regiosymmetry will be different. If you use copper bromide, it will have compound like this. Okay, so I'm not going into detailed mechanism. I will share that PDF with you from where I have taken these examples. You can go through that and you can find out. But what I want to tell you that there are many reagents which will give you your desired compound. Wherever you want to introduce fluorine, you can do that. So advanced organic chemistry has become now. Catalytic difluorination approach. So now here you have seen that there was an alkene and you have only one fluorine atom. At this place you have amine group. Okay, now you can have both the position, both the carbon, you can have fluorine. Okay, this can be done again by selectofluor, and you have to use catalyst like this. Okay, so Jacobson and co-worker have developed an enantio and stereoselective difluorination of cinnamide derivatives. Okay, so you can use such kind of reagent for this reaction. You can have cyclization reaction, either endocyclization reaction or exocyclization reaction. If you have endocyclization reaction, for that this particular compound you can have 6-member ring and you can have fluorine here. Okay, so or if you have exocyclic, then you can get 5-member ring and you have this fluorine here. Okay, so again you have to use your reagent, and you have to use your solvent system very carefully so that to get desired product. Aromatic CH fluorination. Now this can be done by electrophilic reagents. So you have some directing group here. You can convert this. You can have fluorine at this CH position instead of hydrogen. You can have fluorine. For that, first you have to treat it with tributyl magnesiation of aromatic CH. So this is called as a directed orthomagnesiation of aromatic CH bond, followed by electrophilic attack of NFSI. Okay, so this you can do aromatic CH. Okay, for this again I am telling you that there are so many transition metal catalyst compounds are there which can do this reaction, but Ravi sir will talk about that. Okay, silver mediated chichibabin CH fluorination of pyridine and diazines. Okay, so we know that chichibabin reaction we get alpha amine compound at this position. So using same mechanism you can introduce fluorine by using silver fluoride and acetonitrile as a solvent at room temperature. Okay, so if you have this pyridine kind of thing, you can get fluorine at this alpha position. Transition metal catalyzed benzylic CH fluorination. Okay, again I am not talking about sp2 fluorination, I am talking about benzylic, matlab PHCH2. Okay, so this is a fluorination at this position, and you have so many molecules where you have this benzylic carbon where fluorine was introduced. Okay, so this can be also done by using transition metal catalyst. Okay, so you can use such kind of reagent to get benzylic fluorination, fluorination at benzylic CH. Palladium catalyze allylic CH fluorination. Okay, so if you have allylic CH, that can also be displaced and you can have fluorine there. Okay, and you people have used manganese silane, this kind of a catalyst to do this work. Okay, so doing this reaction also you can get fluorine at this benzylic position. Fluorination of unactivated aliphatic CH bond. So if your CH is not activated, if it is not at alpha position of carbonyl, it is not acidic. If it is not at benzylic position, then what to do? Okay. So for that kind of reaction also you can do fluorination reaction, and here there is an example where this hydrogen was displaced and you have this fluorine reagent using again selective fluor. Okay, so this palladium catalyzed aliphatic CH fluorination can be done for this compound. So here you can see that this beta hydrogen, okay, this is a carbonyl compound, this is alpha position and this is a beta position. So hydrogen at beta position is displaced by fluorine. Okay, so it is not activated CH, but still you can have fluorine at that beta position. Okay. So distereoselective beta fluorination of protected amino derivatives, that can also be achieved using this palladium acetate catalyst, and you can have this fluorine here instead of CH. Okay, so such reactions are also there. You can introduce fluorine at gamma carbon also. So you have this alpha, beta, gamma carbon from carbonyl, and that gamma position also fluorine has introduced. So you have fluorination at alpha position, beta position, gamma position. Okay, so in short, you have variety of reagent. You have to find out that what is your substrate, and you want to displace what, whether it is a hydrogen, whether it is OH, whether it is a halide, or whether you have double bond that you want to convert. So number of reagents are there, you can do that, you can use this reagents. Okay, so thank you very much for your kind questions.
Overall, you could see that there is a huge diversity of the reagents, substrates, but the synthetic chemists have advanced, as of now you mentioned that so much that there are many different reagents are available. So this was very interesting review where very diverse substrates. She has covered few examples. Diverse substrates are mentioned. So based on the kind of substrate you are working on, you will be able to plan an appropriate solution. So, is there anything?
And you discuss about task that 7-membered was protected with walk, right? And one more moiety was there, pyrrolidine moiety, that was also protected with walk. But in case of 7-membered, you told about the walk, effect of walk, how it is going to do from this incomplete inversion, from stereo center of hydroxy.
Yeah, I mentioned it is neighboring group participation. Right. In so that?
But you showed one more example where the pyrrolidine was protected with walk. There the inversion was not, it was not there. So
which slide can you please?
slide number was not there.
Yeah, slide number is not there, but
It had a double bond in the ring, so the conformational constraints you mentioned.
In case of task.
here?
No, go back. This one.
One more example like that, you covered about pyrrolidine. Pyrrolidine is protected with task. Sorry, walk. This one. So here, here it is mentioned. And
It was in that process.
You got
That previous slide which I mentioned, in both the substrate there is a bond, but in one there is a double bond. Because of that double bond,
that he got.
conformation